subscribe, leave a like, do something. It'll tell me you like it. Okay. Today we have something really special. Music. There we go. There's music now. Is the music quiet enough? Is it nice? Hello, Koniko. Very special stream today, isn't it? Today. Oh my god, I just bumped over the 3DO. Today, we're talking space. I did lots of research. This will also be a YouTube video, so if you're gonna watch this on YouTube right now, hello. And for my YouTube viewers, keep in mind, I am a hobby. This is a hobby. I am not a professional. I'm not a scientist. God, I wish. This is purely. It's just chilling, right? Yes. I know I could definitely put this in the ASMR category. But then people might get the wrong idea what kind of ASMR I usually do when we're doing normal ASMR. So it's just a little fancy thing. This is. We're only chatting today, anyways. It's just very soft spoken. Space time, indeed. Yeah, I'm not a professional. Everything I say today has been just research, just casual research, just stuff I found interesting. And we got space engine for visuals, and that leads me to my first question. When I'm tapped in here, am I still smooth? Are we still okay? Am I moving nicely? Because space engine is a beast. Space engine is okay, it's running well. Oh, thank God. Because space engine starts lagging like crazy when I tap out. Everything looks good. Excellent. Yeah, I did so much research. Hours and hours of research. Oh yeah, thank you so much for 12 months and another 12 months. Thank you. Thank you so much. Thank you. I had asked you which topics you found especially interesting, so I did special research on those things too. Not all of them, but what came up most. I think once you start nuking, planets might get a little bit much. What? No, this is space engine, not universe sandbox. We're not nuking anything. This is different. No. This is just a simulation of the universe. Treasure train. Oh yeah, that's what it says. That's weird. This is a simulation of the existing universe. Just to watch, not to destroy. Yeah. And I figured we can start out at home. Look, guys, it's us. Look. Look. Do I have you on my screen right now? Can you see yourself yet? Maybe you're over here somewhere. Or maybe it's not even nighttime where you are. Huh? Maybe you're over here somewhere. Look at that. Space time, yes. Wow. Also, doesn't the aurora look so damn cool? Look at that. Look at that. It's insane. There I am. Yay! Look at that. Extremely cool program. Incredible. Yeah, okay, let me explain to you what else we can see here. I have all of the green lines are planetary orbits. I didn't turn them off. I could technically turn them off, but I guess I can turn them off for just a second. Yes, and I have the constellations toggled on as well. Not the lines between them, just them in general. Do you know any space sites? Space sites. What? Do you know any constellations? Hold on. I want to show you my favorite. My favorite is really easy to spot. I'm very basic. Where is he? Hold on. Where is... There's Andromeda. It's Cassiopeia, of course. I'm looking for... Where is he? Ah, there he is. Orion. Yeah, Orion. Orion is these two stars. It's really easy. Actually, I think I'm on my laptop right now. Hold on, we need to turn around. To turn around a little bit. There we go. Huh? Am I stuck? What the hell? Ah, okay. There's Orion. Do you see him? What's happening? Why am I stuck? Hold on, I'm stuck. What did I get stuck on? Hold on. Oh, I landed. Oops. I landed. Wait, how do I get off? No. Hold on. Go to Earth. Come on. Thank you. Okay, there's Orion. Now be gone. There we go. Now we can. There we go. Now I can turn around. Good enough. Yeah, I don't know. Okay. Yeah, there's the belt. Those three stars are the belt. These are the shoulders, and these are the torso. No, hips, I guess. This is the waist. And Orion also has these three little guys. It's really easy to spot. I love Orion. Really cool one. There's of course. Oh yeah, there's a lot of stuff. Aquila, I've learned this one recently. It's a little hard to see when every single star. I think it's. Where is it? I can't tell. I'm not that good at the constellations just yet. I only recently started actively learning. But anyways, let's look at our solar system. Sorry. I wanted to show you Orion really bad. Of course, hold on. Let's go to the sun real quick. Oh. There it is. Looks kind of like our moon. But no, that's not. No, that's an asteroid. What the hell? That's not the sun. Am I stupid? I was about to say, why is it a rock? The sun isn't a damn rock. It's not the sun. There's the sun, I was about to say. I was wondering. That's the sun. I know. I know they're off on purpose because they look really bad when they're turned on. Mind if yeah, I was about to say, what? No. Okay, where is Mercury? Snuggle our friend? Yes. There's Mercury. There he is. Do you guys have a favorite in the solar system? A favorite planet? Well, Earth is the best, obviously, but Mercury is our smallest planet, obviously. Nope, that's Mercury. Mercury is just kind of a sad little guy. Kind of a sad little rock. Yeah. How big do you think Mercury really is? Cause Mercury, first of all, interesting enough, Mercury has the biggest temperature changes, like from day to night cycles, in the entire universe. Mercury is only the size as the United States. It's only about as wide as the United States. I think that's pretty crazy. Except better. And also, surprisingly enough, despite Mercury being like right next to the sun, it is not the hottest place in our universe, which is crazy. Yeah. Let's find Venus. There's a good friend. Where is she? Hold on. Venus. Is that Venus? No, that's a no, that's not what I clicked on. No, I want to click on. No. Oh, I guess that's all. The damn asteroids on it. I will turn them off real quick. Where are my asteroids? Comet tails, atmospheres, nebulae. Ah! No, that's stars. It's clusters. Okay, hold on. We can just make it easy. Venus is also not the hottest place on the Earth. But yeah, here's Venus. Wow. She's very pale today. Also, Venus is basically hell itself. Venus. Let me skip real quick. Venus is hell itself, basically. If you stranded on Venus, my condolences. Venus has a 19-kilometer thick atmosphere of pure battery acid. Of literally pure battery acid. Sulfuric acid to be precise. 19 kilometers thick. The pressure is insanely strong. It's like 900 Fahrenheit on the surface. They actually managed to land a spacecraft on Venus once, and obviously the spacecraft died immediately. Oh god, a picture for you. Look at this. This is Venus. That's a real image of Venus. Looks friendly. Horrific place to be in. Really bad place to be. Yeah. Died almost instantly. Very. I heard it's raining molten iron over there. Could very well be, yeah. Doesn't it rain glass sideways? I'm thinking of Jupiter's moons. I think that's Jupiter. I don't think that's Venus. I'm not entirely sure though. But yeah, it's got big volcanoes too. Yeah, and no moons. This guy is alone, forever alone. She is a strong, independent woman. No, I'm kidding. Let's find Mars. Where's Mars? Mars. What is this over there? That's planet Earth. Okay, no. What's that? That's an asteroid? That's not Mars. So yeah, that's Jupiter. I wonder what that thing with the 10,000 moons is. Where's Mars? I keep clicking on asteroids, it's really annoying. Planet Mars, I found it. Let's go there. No, I clicked off it. But I found it. There we go. Go there. There's Mars. Oh yeah. That's the place they want to put us on. I need you to know, and this is really embarrassing, for a very long time I thought Mars was much bigger than Earth. I thought Mars is much bigger than Earth. No, it's not. No, not at all. I don't know. I don't know why I thought that. Yeah. Mars got its two cute little moons. Two little guys. And we've got Phobos, and we've got... Where's the other guy? Hold on. Oh, there he is. There he is. Yeah, and Deimos. You can go to them too. Look! Rock! Big old rock. Big rock. Big rock. Big. Terribly good to go so some of these planets. I mean, yeah, it's just an emulation. Rock. Yeah. Mars has 37% less gravity. So you'd be like super light on there. So that's pretty cool. If there's a rock on the floor, I'd take the bad boy home. It's a nicely shaped rock. Look at that big cliff there. What the hell? What happened there? What slammed into it? We will never know. Mars also has the largest volcanoes and mountains. Now, I wonder where Jupiter is. Oh, that's Saturn. Hold on, there's Jupiter. Now Jupiter is a big friend. Big friend. There he is. Got a ton of moons. Lots of moons. Thank you so much for being here. Jupiter's our shield. Don't steal my light. Did you guys know that this spot right here, that thing, that's a big storm. That's not like a physical formation or anything. It's just a ginormous storm raging. One day it'll be gone. One day it'll end. And then Jupiter won't have its big storm anymore. And this storm alone is as big as the Earth. That's how big this guy is. Big boy. Yeah. Also, if I am correct, Jupiter's moons are the most likely place in the solar system to have life other than Earth. Microscopic life, obviously. But there's quite a few theories. Yep. Well, maybe not this guy, but oh my god, look at this. It's so shaped. Why is it shaped like that? Okay. But yes, Jupiter's gravity is the reason why we can still exist today. Because obviously, we're traveling through the universe always. And there's lots of asteroids, lots of everything really. And Jupiter is so massive, so big, that it attracts all of those big dangers. And they fall onto Jupiter or their orbit gets disturbed in some kind of way. And that's why Earth is still standing today. Hmm? Everybody say thank you to Jupiter. There's a lot of theories that Jupiter was supposed to be a star at some point, but no. Jupiter's not a fail star. Not at all. I think for like the smallest existing star, you needed like 13 Jupiters. So no. Alright. Where's Uranus? Hold on. I can't see shit by the moment, so I'm just gonna search. Go there. Can we see Titan? Oh. Hold on. We can. That's on Saturn. When we get to Saturn, yes. There's this guy. Uranus. Yep. Are we all going to be are we all going to be mature about this? No, we're not. Okay, I see. Yeah. It's this guy. Yeah, get it out of your system. Okay. One thing I found out about Jupiter, which actually not Jupiter, Uranus, that I think is horrifically funny. Uranus smells like farts. It's it's very unfortunate. Oh my god, yeah, right? That's yeah, it's a very stinky planet. Like unironically. Hold on, what was it again? Wait. Why does Uranus? It smells like rotten eggs. Cause of hydrogen sulfide. Yeah. Uranus is big. Uranus is a big guy. It's one of the gas giants, I'm pretty sure. Right. Yeah. No. Ah, it's an ice giant. Nope, I'm mixing them up, sorry. It's an ice planet. Just got a lot of ice. Well, sulfur is incredibly stinky, yes. Would it make it more like rotten eggs? Yes. Yes. True. Also fun fact. It's got rings. Did you know that? Hold on. This is what they look like. This is an actual image. Look. It's got rings. 9 of them. No, 13, not 9. 13 rings. It's got 13 rings. I don't think they're in this. Oh no, wait, they are totally in the simulation. There they are. Don't you see them? There they are. Uranus has rings, yes. There they are. They're just really hard to see. Are those moons? I can't tell. It's a little hard to tell in this. Either way, it's got rings. Yeah. And also really fun fact, in comparison to every other planet, its axis is tilted so that Uranus basically rolls around the sun. Like it's continuously rolling around the sun. Little rebel. But yeah, and there's a theory that the reason why it went tipped over is because a huge thing crashed into it. About the size of Earth. Maybe. We don't know, it's just a theory. But yeah, cool boy. Cool big guy. Big guy. Next, Neptune. Where's Neptune? Neptune. There we go. Let's go there. It's the same theory with our axis. We have a small tilt. Yeah. There's Neptune. Neptune got big auroras. That's crazy. Yeah. Yeah. Neptune is a very big guy. Very dense guy. Very cool. And oh, wait, really? Oh yeah, Neptune has rings too. Neptune also has rings. They're just really hard to see. Look. Look. She got rings too. Yeah, on Neptune, it is so dense. The atmosphere is so strong, it can rain diamonds. No, because of density pressure, sorry. Again, science words are kind of hard in English sometimes, I keep mixing them up. That's when only Earth doesn't have rings. For real alone, even on a cosmic level. But we're not, we have a good friend. Tells me human would be under a lot of pressure there. I think so too. Well, yeah, that's Neptune. Then of course we also got. Did I not? Really? Did I forgot to write anything about Saturn? I forgot to write about Saturn. Let's go visit Saturn anyways. What? I forgot Saturn? That's really funny. Oh my god. Hey, guess which? Guess which planet in the universe has the most moons? It is Saturn, yes. As of confirmed as of March 2025. This is a recent discovery via Saturn has a lot of moons. A lot of everything. I think this is really well known, but oh, first of all, Saturn is so light and actually way less dense than water is. So if you had a big enough pool, you could throw Saturn in there and it would float. It would float. I think that's pretty crazy. Can I not turn off moons? I probably can, I just don't know where. Can you imagine a planet our solar system won't be without Saturn's rings? No. I don't think it would be that bad. But he is an actual gas giant, obviously. And we are actually really lucky because Saturn's rings are not permanent at all. In a couple hundreds of thousands of years, I think it was, they'll be gone because they're raining onto Jupiter. They're raining down, not Jupiter, Saturn, sorry. All of the rings rain down on Saturn, slowly but surely. And now, I included, because I felt like I might get attacked if I don't. Let's go look at Pluto. There he is. Yay! Pluto! Yay! There's the guy. This one, I'm trying to upgrade from gas giant to something more solid. Yeah. Pluto's moon? Where is it? What's that? It's the red thing. No idea. Where is the guy? Must be it. Yeah, Pluto has a moon that's almost as big as Pluto itself. Oh yeah, look at that. Almost. And they're kind of, it's Pluto has kind of a wonky orbit. It's not as like stable as with every other planet, and yeah, the moon and Pluto, they're tidally locked. So they're always looking at each other. Always, always. Our own moon is even bigger than Pluto. It's a small guy. Small guy. It's also not actually the furthest away planet in the solar system, depending on where in orbit Pluto is. Sometimes it gets closer, sometimes it gets further away. It really depends. So, that's our solar system. Now we are moving on from planets. Now talking a little bit about our planets would be a good introduction. Just a little startup. Okay. Next I got. Do you guys know how stars are formed? I don't. Now I have a lot of stuff written down. Stars are formed from big clouds, molecular clouds. They are thousands to millions times the mass of the sun and span sometimes hundreds of light years. Not necessarily nebula, no. Nebulas can lead to new stars forming, but obviously nebulas are not the only clouds that stars have formed from. Because for there to be a nebula, there had to be a star first. And if all stars came from nebula, then where did nebula come from? So like a certain state of clouds? It's a certain, yeah. Big clouds form them. They're very cold and very well. There's a lot of gas, obviously. Hold on, let me scroll down. I made more comments about that a little later. Did I not? I guess not. But yeah, they're formed from clouds, and it's really common that more than one stars form in like from the same clouds, which can result in star systems with more than one star. Like for example, Capella. Capella is not only a binary star system, Capella has even more of them. Capella B, Capella H. Where are the other ones? I need to back up a little bit. Oh wait, no, I need to get closer. I'm not that close. Where are the rest? Where are the rest of you? But yeah, binary star system. Seems to be sleepy here, there. Binary star. They are really cool. Get closer. Can I get a little bit closer? There we go. That's what I was looking for. Look, that's one star. Where's the other one? That's too fast. Yep. Several stars, and they pull like each other. The gravitational, like the gravity. So big system. See, there's another one. I think it's, how many stars is that? No, I have no idea. Like 4? 5? Look at that. They continuously orbit each other. But the other stars in the system also pull at each other. Which is a big old clump of stars. Also, there's different categories of stars. I got some example for several of them. And they're separated by color and luminosity and like size, obvious. The hottest guys, real big guys, so real big boys, are O-type stars, like it's also a binary star system. Yeah, they're really common. That's a really big bright star. Look at that. Blue subgiant. Might not be the best example, but that's okay. Yeah, they're very bright, very hot, very hot. So extremely hot. Yeah, and they're very blue. And just straight up blue. Could you imagine if we had a blue sun? Wouldn't that be cool? I think that would be pretty cool. Yeah. I don't know how big? 33,000 Kelvin. That is 32,000 degrees Celsius. Yeah. It's really hot there. Would suck to be stranded there. So it won't matter much at 33,000. Yeah. Those are O-type stars. And then we go down from there. Then there's B-type stars. I don't know why B-type stars are before A-type stars, but they are. To me that makes no sense, but sure. You guys ever heard of Liget? Liget is also a big boy star. That's a huge boy. Huge guy. Look at this thing. Look at that thing. Liget is huge. B-type stars are bluish white. And they range from 10,000 to 33,000. That's like a pure white circle on my monitor. Yeah. They're bluish white. Bluer than white. There's also like white ones. A white star, for example, is that one you definitely have heard of. Sirius, which is the brightest star outside of our sun we have in our own sky. That's not because it's necessarily the brightest of all of the stars we've ever known. That's not what I clicked on. Who are you? Whoa, look at this. That's a procedurally generated object, isn't it? No, it's a real object. That's crazy. That's crazy. Are the planets real too? Hold on. First of all, these guys aren't on fire. Procedurally generated. I thought so. Let's go back to Sirius. It's the most distant object in this program. Oh, it generates. I don't even know. This thing can generate space. You can go very far away. There's no way to reach, like, the edge of the universe or anything. Such a thing. But yes, Sirius is pretty close by, I'm pretty sure. How far away is Sirius? Sirius is... all of these stars are part of the Milky Way, by the way. Just distance above. Am I stupid? Oh yeah! Well, I don't know what that is in light years. It's only 8.6 light years away. Yeah, but 8.6 light years is a lot more comprehensible than whatever that is. That doesn't say the light years. It's a big boy. I can do the math. I can't do the math. I'm not good at that. Then after A, there's F-type stars, which are yellowish white. So now they should get whiter. No, wait, not whiter. Yellower. Let's go there. There he is. They're all binary systems. I didn't even check that before. That's really cool. Yep, more yellow. Jeez, I don't travel the light years, so I can't see for sure. It's cold. Out in space, of course, it's cold. Yeah, kind of looks like a light bulb. F-type stars are between 6,000 and 7,300 Kelvin. Hot. Still really hot, but like, you know. And after F-type stars, we got G-type stars. Whoever named these classes needs to go to school again. What? What is the next letter G? And do you guys know the most famous star that is also a G type star? It's our sun. It's our sun. There she is, back home. But Capella is also a G-type star. Well, one of them. Don't ask me which one. Yeah. These are 5.3,000 to 6,000 Kelvin. And now they're getting more red. The colder they get, the redder they get for some reason. Don't ask me why, I don't know. I don't have... Do I not have this guy? I don't. Okay, unfortunate. But yeah. I should be able to... Yep. See, they get much more orange. It's a small guy. Smaller guy. Okay, and now I want to show you a type of star I think is really, really cool. Yeah, no one is over there. It's our neighbor. Hi. Have you guys ever heard of a full-Rayet star? Well, Rayet stars are really rare, guys. Let me go. Oops. Oh, I think. Am I landing on it right now? That was not my intention. Where am I? Eh. Hold on. I did land on it. That was not my intention. Yeah, World-Rayet stars are massive and very short-lived stars. This is Space Engine on Universe Sandbox. No, we cannot make something complete. This is just to look at. It's a stage right before stars go supernova. They basically, before the star goes supernova, they start shedding their outer layers, which you can see really nicely here with those like blue things. Blue star sheds blue stuff. Wow. Yeah. Only a couple of, not every single star that goes supernova goes into the Wolf-Rayet's state. No, this is not. You're thinking of a different program. No. This only generates the universe to explore and look at, not to mess with it in any way. That's a universe sandbox. Imagine looking directly at that. Imagine. Your Wolf-Rayet stars are very, very short-lived, obviously. This is right after it goes supernova. Hold on, I even got some pictures for you. This is what a real Wolf-Rayet star looks like. Look at that. You can see the shells of gas and dust. Some being expelled. You can even see that it's not like a continuous stream. They're pretty cool. Really, really cool, guys. And again, they last not very long at all. And all of this gas, all of this material will one day form a new star, and it all starts over again. Okay. People also asked me to talk about different kinds of galaxies. So that's what we're going to talk about next. Yes. So, there are several types of galaxies, of course. The most famous one. We can look at our cute little neighbor. Where is she? Hello. Can we see Andromeda? Right now I don't see much at all. Let me back off a little bit. Can we spot our good old friend? Hold on. I cannot see her. Why does it start looking elliptical? Because it is elliptical. Again, it's shedding. I can't see Andromeda. Andromeda. Do you guys know what type of galaxy Andromeda is? Galaxies are classified by their shape. That's really all. Only their shape matters. Yes, Andromeda is a spiral galaxy. I think that's pretty. That's really cool. Pretty obvious. We've got the center, which is called the bolt, which is made up of older stars. Well, really, the further you go out, the younger stars get. If you see something that is bluer, it's newer, usually. The disc are, the arms are called the disc. And it also has a halo, which is on clusters of stars. I'm not sure if you can see it well here though. Andromeda is really interesting because there's like another small galaxy right next to it. Where is it? I think it's up there. Hold on, let me go. Can we get that? Ah, yeah. This guy is gonna talk about spiral galaxies for a little bit more because there's different kinds of spiral galaxy. There's also barred spiral galaxies, which have bars in them. I'm not joking. They have like a little. The Milky Way classifies as one of those. Hold up, can you see that in this program? Let me see. Well, I guess a little bit. Can you tell? There's like the center is like a tiny little bit elongated, and yeah, the notifications will be quite loud. Sorry. Hold on, can I get like a real picture? They can look like this, or you can see it really clearly, like one in between. But they also have different classes in between them, depending on how many arms a spiral galaxy has. There's some very few. There's some very few. For example, oh, that's a big picture. I can't put that on screen. Yeah, here's a very very direct image. I can go from having lots of arms to just 2. I think if it's below 2, then that doesn't count as a spiral galaxy anymore. Needs 2 arms. At least. Yes, I think spiral galaxies are the ones that are the most well known. I mean, we live in one. Okay. The next type is, like I said, they tend to look the prettiest. Not true. Elliptical galaxies are fat little guys. Yep. They're like eggs, kind of. Well, not always, but usually they're like egg-shaped. They can be round, but they're usually pretty eggs. Yeah, the stars here wrap around the galactic core equally, and they spread out also equally, which creates this kind of shine to it. They can be anywhere from like really round, just a ball, to long. This is the long boy. Look at that. Long little guy. That's a very weird egg. Then there's also irregular galaxies. And irregular galaxies are really like, well, they can be anything. They can be pretty much any shape or form. They're usually pretty small. Like here, this is a galaxy. This is a galaxy. It just looks like a bunch of, I don't even know, stuff. But no, that's a galaxy. Oh yeah, galaxies are classified by a couple million to a couple billion, like an ensemble of stars. And usually, as obviously most people know, usually there is a black hole at the center. And the irregular galaxies also have some, but many do not. Yeah, that's probably because of their shape. So not every single galaxy must have a black hole at its core. So that is not like necessarily important to. Also, hold on. Nope, I'm trying to. I think if I do this, we're gonna go to this topic a little bit. Oh yeah, it's generating. Give it a moment. We can look at do you know what that is? That's the black hole at its center. You can see the time dilation and everything. We're gonna talk about black holes later again. But yeah, there they are. Oh, there it is. Andromeda does very much. Let's go back to. Cool effect they got there with the warping. Yeah, it's really, really nice. Let's look at the lovely video real quick just to get this off my screen so that my PC doesn't explode. I think it'd appreciate that. But yeah, then we also got dwarf galaxies, who aren't all that interesting. They're small galaxies, very small ones. And there's also starburst galaxies. Have you guys heard of those before? I found my. Hold on. Starburst galaxies are galaxies where a lot of new stars form. There's a lot of gas, and like it's defined by the rate at which it produces new stars. And the Antenna Galaxy is one example. Look at this thing. This is two galaxies, look. But from Earth, they look like a heart. Isn't that just the coolest thing ever? Look! And that's a real object. That's a real thing that exists. Hold on. Little heart guys. Your little heart guys. Oh yeah. And as you can see, there's lots of gas around it, which forms into new stars. There she is. There she is. That's the real object. That's the real thing we have in space. That is a real thing that exists. But yeah, there's tons of starburst galaxies. They have a large quantity of gas, as I said, and it's converting this gas actively into new stars. That's pretty much all. These are like these are interacting galaxies too. That's another type. These are galaxies that I have nothing written down about this. Wait, I have not about starbursts. Okay, I got confused. So basically, starburst galaxies often form when two galaxies start merging. And I mean, that makes sense. That's why they have these trails too. They came really close to each other, and now they're gravitationally attracted and colliding. Like, these two are actively merging. I think that's pretty obvious. And that can disrupt a lot of things. They can set a lot off. And that's why there's so much gas that can form into new stars. Tidal gravitation forces, a direct collision between gas clouds, compress gas within a galaxy. And then that gas rapidly forms stars. Oh, rapid! It still takes ages, but like, you know what I mean? And yeah, so I don't think they don't stay in starburst galaxies forever. One day they've used up all their fuel galaxies wrapped on the universe time scale. Yep. Hmm. Then we got lenticular galaxies. Now, lenticular galaxies, what do you think those are? Do you know what I've noted for lenticular galaxies? Snorkel. Snorkel. Anyways, here's the cartwheel galaxy, which is actually two types of galaxies. Hey, there's two little guys over here too. Yes, lenticular galaxies are round. They're round and blue. And they're pretty uncommon. And there's also ring galaxies like this guy. Ring galaxies look like they have a ring around them. I think that's pretty self-explanatory, really. They look like this in real life. See? See? It's got a ring around it. What's also very crazy about this specific image is that this rare type of galaxy seems to have another ring galaxy, like kind of like in its ring, which is like crazy coincidence. Which is like way further away. Very circle. Yeah, this is two types of galaxies at once. Why? And then there's also ultra diffused galaxies, which are just dim. And just very, very dim old galaxies, which I also found really funny. Diffuse galaxies either have a lot of dark matter to the point of some diffused, like ultra diffuse galaxies being like 100%. And this is really what I read. This is exactly what I read. Some are consistent of only dark matter, and some have none. What a nothing statement, really. Wow. So, either it has dark matter and it doesn't. They don't even know if dark matter exists anyways. Yes, that's a theory. It's just a theoretical thing. Yeah. And interacting galaxies, those are my favorite. I showed you my favorite just now. Hold on, there's the Whirlpool galaxy, which are very obviously two interacting galaxies. Their interacting galaxies can crash into each other. They can merge. They can pass each other and tidally affect one another. Not tidally, like gravitationally affect one another. They kind of tear at each other. They're very beautiful, aren't they? I think interacting galaxies are the prettiest. I think they're so very cool. Look at that. I hope there's no civilization in there. That must suck. Okay. Now we got to the point I did the most research on, because you guys are most interested in those. Now we are going to talk about the life circle of stars. Do you guys know what this guy is? That's Beetlejuice. He's about to go boom. He is about to go pew. And we're gonna see it from Earth one day. Well, he's probably already gone. Why does it look like a lump? Because it is a lump. Because it is a lump. Almost supernova, yes. Yeah, he probably doesn't exist anymore. And the light still has to travel to reach us. But do you know what exactly decides if a star goes supernova or not? Because not every star goes supernova. And what happens to your star after it? Okay, hold on. I have a lot written down here. So, obviously, every single star lives millions and millions to billions of years, depending on its mass. And its mass, it's its fuel. Which is really, really important. Like, the mass of a star is basically, that is the main thing that dedicates what it becomes. And it's really crazy because basically the way stars burn is because their gravitational pull is so strong that you know how magnets, like you cannot make a positive magnet meet another positive magnet, like both sides, they repel each other, right? And what makes stars burn is basically that the nuclei inside of them, the gravitational pull is so strong that when two positively charged nuclei meet each other, they collide instead of repelling, which results in nuclear force taking over and them fusing, and that creates energy. Massive amounts of energy. And only a star is capable of doing such a thing. That is what defines a star. Fusion at its core. I mean, and that's why they need to be so massive, because without that mass, they don't have the same gravitational pull, which means that they can't fuse. They can't create the energy that makes them stars. So we're gonna talk about low mass stars first, and then what's a low mass star? Surely there must be one. That's a red giant. Can we get a small one? That's a bright giant. White main sequence stars, bright giant, orange giant. There we go. Dwarf star. Yay! Is this a real object? Real object. Crazy. Yep. This is a lower mass star. The lowest a star can weigh is around 13 Jupiters, and these begin as stars, as clouds of gas and dust spanning several light years wide. So even the smallest ones are still, they form huge things. And the gravity in those clouds puts them together, and eventually it gets dense enough to form a star, and it starts fusing. It's a star. Yay! There you go, you got a star. Yeah. And its life, it performs, it fuses hydrogen atoms into helium atoms. Yes. And it just does that for a really long time. The cool thing about stars is that the smaller they are, the less mass they have, the longer they live. I think that's crazy. Because you'd think the other way around, right? But no. The bigger... Thank you for the follow. The bigger and heavier a star is, the more material it has, the more gravitational pull it has. And so, in turn, it fuses faster. It burns through its material much, much faster. So, bigger stars don't necessarily have longer lives. That depends entirely on their mass. But yeah, eventually it'll run out of hydrogen. Well, okay, at this point we're at the it's almost running out of hydrogen stage. Yes, almost, just almost. And after that, its core starts to shrink, which causes the hydrogen fusion to be even faster, which makes stars swell. So they get bigger and bigger and bigger. And as they get bigger, they also cool more and they become red. And it stays like this for like another billion years or so. It stays in that stage for another very long time. And once it's big and hot enough, like in the core doesn't cool, the core does not. The outer layers do though. Once it gets hotter inside and heavier, it starts fusing heavier materials too. So now it has more material to burn through. And at that stage, the star starts pulsating. It shrinks a little bit, swells up again, you know. And eventually, it shrinks and becomes bluer. And once most of the material has burned up, the core collapses. And when that core collapses, once more it swells, and with that swelling, it pushes its outer layers back into space, leaving only the core behind. Just a sad little guy. Just a sad little guy behind. Can we find a white main sequence star? Orange dwarf. Can we get a white dwarf? No, these are all big boys. Giant, 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 giant. These are all big boy stars. Unfortunate. Hello, hi. Probably doesn't smell good either though. Probably not. But yeah, do you guys know what the outer, the shedded layers of a dead star form? Those layers. Oh, where is it? Where'd it go? Do I not have it on? Ah, there we go. They become nebula. They become nebulas. Do we have... And yes, nebula can eventually fuse into another star. Hold on, let me you guys know about the Butterfly Nebula? I think that one looks really cool. Butterfly Nebula. Yeah. Oh, it looks so sad here. It looks much cooler IRL. But yes, every single nebula is just remnants of a star. Remnants of a big dead star. Yeah, nice. That's a very big picture, but that's okay. Here she is. Look. Look. This used to be a star once. That's what they leave behind. That's where they come from. Okay, now after yes. Now we can move on to higher mass stars, which are funny guys. They're a lot more interesting in terms of what happens to them. Let's find a nice big star. Oh, that's a cluster. Hold on, wait. Clusters are really cool too. Look! Yeah, cluster is just... okay. What is this? Is the cluster generated? Clusters are just a ton of stars. Not big enough to be a galaxy or anything. But main sequence Can we get a big guy? You're looking worth. Are you kidding me? Now we're not finding any big ones? It's really funny. Sure, let's go there. Let's go to you. Star. Let's zoom out a little bit, just because it's pretty. Okay. Bigger stars. Hi, thank you. Okay. Big stars essentially start out the exact same as small stars, except that the cloud they come from is bigger, way bigger, huge. Okay? So, what's important to know, like I said earlier, the more massive a star is, the more mass it has, the stronger is its gravity, and in return, the stronger its power is. Because of course, the more it makes sense. Which also means that it burns way faster through its material, and they die within only a few million years. All of their stages are fairly quick. So those huge stars, they're just not stable. They die pretty fast. So, as it ages, a star starts swelling just like a little star would. But since the pressure in its core is so much higher, it can fuse even heavier elements. So you can kind of imagine it like a matryoshka doll. Like at its very center, the gravity is the strongest, of course. So that's where the heaviest elements can be fused, and then it has like layers and layers and layers, right? And the center of it is so strong it becomes iron. That's the heaviest material it can fuse inside of itself. And this is where it gets really interesting, because this iron core is so stable that once all of the material has burned up, no more fusion takes place, and the star collapses within just a second. A singular second, can you imagine that? ginormous thing like that just bam, and that triggers a supernova. Every single heavier element, like silver, gold, everything, all of it either came from a supernova or an event of similar, like, gravity, like, what's the word? Like, big events, really big events. All of those things came from either supernovas or collisions of neutron stars or black holes and neutron stars. Something like that, yes, similar scale. Absolutely everything. You and I are made of stardust. Everything around you that you can see has come from stars. One day. Isn't that insane? Everything around you, everything you ever put inside your body, everything you've ever interacted with comes from outer space. Everything. Okay. And a supernova gets so bright it outshines its own galaxy. It's that crazy. If we ever have a like supernova happen pretty close to us, like in our Milky Way, then we will be able to see it with our naked eyes. The Grand Nebula supernova was actually recorded by many civilizations in 1054. Yeah, I said that right. They reported that like a big bright spot happened, like suddenly appeared out of nowhere. It was visible for several weeks, I think. And now is where it gets really interesting, because a supernova does not leave behind a white dwarf. That core does not just cool and just sad and alone, just kind of, does its thing. The remnants of like a low mass star, like that core that gets behind the white dwarf, that still fuses inside of itself, by the way. It still fuses material. It doesn't stop for a very long time. It's just way smaller and way less powerful. A big boy star does not do that though. The mass of the left behind core is what determines its fate. This is where it gets a little bit complicated. I'll do my best to explain it. So, if the core is anywhere between 1.4 million to 3 million solar masses, and can we just talk about how the crazy that is? What do you mean millions of solar masses? What? That's crazy. If it's between 1.4 million and 3 million solar masses, the core will collapse and everything inside of itself will fuse into neutrons. It's just one ginormous, dense pile of neutrons. And during this collapse, hold on, I can first wait. Can we go there, please? Yes. Okay. Yeah, very okay. Alright, but you can see it here. Do you see it spin? Do you see it spin? It spins real fast, right? Okay, during this collapse, the stars start spinning faster and faster and faster and faster, which forms a really, 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 really powerful magnetic field. And That's the stage where the core starts fusing neutrons. And as any fusion does, that releases energy. Lots of it in the form of neutrinos. And eventually, everything inside of the core presses so tightly that those neutrons collide. And in that moment, everything stops. Like the stars, it stops. Nothing moves anymore. It just halts at once, and this creates a shockwave and expels the star's outer layers and neutrinos, and that's a supernova. That is what a supernova really is. It's a shockwave. And once it's expelled its outer layers, that core becomes a neutron star, which is not where it ends really. They're usually only around, like, they're small, they're really small. They're only like, is it up here? Spectrum, distance, system diameter, system, okay. Oh yeah, it's a triple, okay. Can I get closer? No, okay, that's fair enough. Yeah, I don't know what. Oh yeah, see, they're really small. This thing is only like 20 kilometers. It's only about 20 kilometers wide. Isn't that's insane? They're really, really small. Yeah, one singular teaspoon made of a star would weigh 10 million tons. One singular teaspoon. Which is insane. Also, it starts spinning again. I don't. Now it starts spinning again. Since it's so extremely small, it can spin fast. Like, and you think, like, in the context of like space, okay, fast spinning, what's that? Like the Earth takes 24 hours to spin around itself once, right? So what could classify as fast? Spinning once, like every hours, couple of minutes. No, this fucking thing can spin several thousand times in a second. What? This thing can potentially, it's anywhere between like a couple times a second or a minute or something to several thousand times a second. That's I think I read something earlier about if you put like a car had wheels that spun that fast, it would go 7,000 kilometers per hour. And okay, this is really hard to explain. This is all like really like, there's a lot of physics involved in this. I hope I'm making this easy enough to understand. But yeah, its density and size dilates space and time, creating a similar effect like a black hole. You can see that here too, can't you? Do you see it? See it? And I even have an example of what it looks like the magnetic field. What did I put that? Oh yeah, here. This is what this magnetic field looks like. I'll leave it up here. Should I talk about it a couple of times? It's 10 times the speed of sound. Yes. Yes. Okay, so fun fact. If you go inside the core of a neutron star, like inside of it, the neutrons are pressed closer and closer against each other the deeper you go. And this material, scientists have called nuclear pasta. Because it's kind of like different pasta types. destruction of humanity. Incredible. Did you guys want some nuclear pasta? Hell yeah, man. But yeah. So back to when a neutron star starts forming, okay? Something called spaghettification. Yes, that's a different thing. You would get spaghettified if you fell onto a neutron star, that's true. But that's not what we're talking about right now. But yeah, back when it forms, big strong magnetic field, right? You can see it up there. That's a kind of visualization. It dilutes everything around the vacuum itself. And it's a little bit like a magnet, so it has two poles, right? The magnetic force exists. The magnetic force exits on a north pole and enters from a south pole. And these poles don't usually align with this actual rotation axis, so kind of like wobbles. It's weird. So it spins and it pulls and it spins some more, and since the poles is like basically the only places where stuff can exit it, it has these streams coming out of it that you see there. Like, you see them? And here's something really, really interesting. A star's luminosity is usually pretty stable, okay? Like, a star is not gonna... The reason why we see stars flicker in the sky with our own eyes is just because of disturbances in the atmosphere, not because the stars actually flicker. But when scientists looked at it through different wavelengths, they saw things that twinkled, but they flickered really irregularly, kind of like a metronome. And those are pulsars. Those are these things. So I'm not quite sure. Hold on. So every pulsar is a neutron star, but not every neutron star is a pulsar. Yeah, not every single one of these emit those beams of radiation. So yeah, not if they emit those beams, then it's a pulsar. If it doesn't, then it's just a neutron star. They do not automatically have to do both of these. And this also probably makes you wonder, hey, but what are those gamma ray bursts I kept hearing about? So these are really complicated to explain. I tried understanding it, but it's a lot of like physics stuff. So okay, gamma ray bursts. So you know that there's the electromagnetic spectrum, right? There's electromagnetic waves, and lower energies of electromagnetic waves are stuff like radio waves, microwaves, that kind of thing. And higher energy stuff is things like X-rays, right? And the highest end of it, the highest this energy can be, that's a gamma ray. That is what it is. It's basically like pure radiation. So if you would get hit with a gamma ray wave, your DNA would crumble. It would just get destroyed. So like big, fast, strong, wiggly wave. It's radiation, right? Yeah. Okay. And we actually, like, Earth gets hit with gamma rays a whole lot. Yeah, it is a little wave. But we're really lucky because we have our atmosphere. We have the ozone layer, and that filters out all the gamma rays. Wow, we're saved! Yay! Yeah. And gamma ray bursts are, like, gamma rays in general, are the brightest thing in the universe. They are the brightest thing. It makes sense because, like, you know. So there's two types of gamma ray bursts. one is long and one is short. When you think of it, like, oh, okay, long ones. How long are they? Like several thousands of years, maybe? No, they're a minute long. The longest the gamma ray burst can be is like a minute. And the short ones are like just a second. It's like lasers, basically. Kind of, yeah. And these rays, they're very precise too. They're expelled while either two neutron stars collide and form a black hole, or something else, and I didn't write that down. Incredible. And here's the kicker. We detect about 1 gamma ray burst per day. What? But they're all way too far away to hurt us. If something close to us fired a gamma ray burst at us, we're cooked. We're just dead immediately. We would never know either because it moves at the speed of light. There would be no warning. There would be nothing. Nothing. It's dead. So, okay. Now there's one more thing. There is one more thing. Of course. Because I said, if you remember, neutron stars form if the mass of a core is between 1.4 million and 3 million solar masses. So what happens if it's above that? So, okay. Basically, once this core is above 3 million solar masses, gravity cannot be stopped. There's nothing that could, and when the core collapses, it forms a black hole. That's how they work. The core collapses into a singularity, and it is a mass of pure gravity. And the reason why we cannot see black holes, hold on, let's see, is because it swallows neutrons, which, like, nothing can leave it, obviously, which is what makes us see. Not even light escapes, nothing, nope. Let's look at our nice little, hold on, it's loading. Let's look at our black hole. Ours is dormant right now, by the way. Apparently, I don't know how that makes sense, but apparently that's what it is. Oh my god. Oh. Okay, I don't know what just happened there. What the fuck was that? Can we go to our black hole? Not land on a neutron star and appreciate it? What the fuck? Did you just land again? I think so. There we go. Where is it? Is it that? Yes, Sagittarius A. There it is! There it is! It's our friend! It's our friend! Oh yeah! Okay, going any closer, so I think I'm good. It's a little dangerous. There it is. Black hole. Our black hole. That's ours. Yay! That's the one that keeps us centered. Wow! So that's how those things form. That is all I researched. Hold on. Yep. That is all I researched. Do you have questions? If you fell into a black hole, that would be bad. That would be really bad. Don't do that. That's bad. That would be not good. No, don't do that. No. Sensei, can you show Titan? I can't show Titan. There is Titan. Quasars? Ah, okay. Quasar is a black hole that shoots out electromagnetic. Do you want to see a cool thing? Hold on. You can mess around in the settings here. If you turned on comets and asteroid orbits, like you can see the planetary orbits right now, right? Look at what this would look like if you turned on asteroids. Yup. I got a lot of asteroids. What's the largest sun? What's the largest sun this has on record? Like the largest star? Well, this procedurally generated one, so. Oh god. Red luminous supergiant. Yep, that is the biggest star in the universe that we know of. Anyways. Oh my god, look at the thing. Oh my god. That indeed is a big boy. Big boy. Huge guy. Insane. Yeah. Does it have the biggest black hole? Oh wait. There it is. I'm blind, turns out. There it is. Jesus. It does have it. Oh my god. That is indeed insane. Yeah. Well, yeah, these guys aren't really that stable. I'm guessing that's why. Oh no, did I land? No, I don't want to land. No. Thank you. Does it have? Let me look up. Ton. Which one is it? 6, 8. Guess it's the galaxy it's from. Ah, this is a quasar. Okay, hold on. It's loading. We're traveling. We're getting there. Oh my god. Oh god. Okay. You can do it. Huh? No, we're in the piss cloud. Where is it? What? I don't think they can generate this. Ah, no, there it is. Go. Nope, that's just sent me out. Okay. Sure, that works. Is there anything else you want to see? Do you guys know what one of my favorite objects in the sky is? I love the Pleiades. Oh my god, I love these guys. I don't know why, I just do. Look, the 7 sisters. I think they're really cool. Look. I just really like these guys. I can't tell you why. They have a lot of gas and dust around them, which makes them like glow nicely, even in the night sky with your bare eyes. Oh, that reminds me. I've talked about this plenty before, But do you guys know just how big Andromeda really is in our sky? This is Andromeda in our night sky right now, right? There it is. So you can see it with your naked eye under good conditions. I've never seen it before, but it's possible. But if Andromeda was brighter, then it would look like this. It's much larger than the full moon in our sky. If only. It's a big boy. And Andromeda and the Milky Way are approaching each other. They are getting closer and closer. And one day it's very possible we might merge. We could also completely miss each other, by the way. Recent studies apparently said that there's no real guarantee that we're going to merge with Andromeda eventually. But if we do, this is what we're going to see. These are actual illustrations from NASA. Come closer and closer and closer. Have you read the lore in Andromeda Greek myth? Yeah. At some point. One day. Well, we will never see this. We will never ever see this. But it's out there. One day. Actually, it's still closer, brighter, but everything is so far. It's probably why we stayed outside. Stayed safe. Yes. Andromeda. Yeah. Wouldn't that be sweet? I think that would be pretty cool. Okay. Any more questions? Oops. Any more questions for today? Is there anything at all? All spaced out.